Matthew Sandoval, and this is Lab 2, Lines of Charge. Here are the contents of the lab: introduction, experiment, code, discussions, and conclusions. The purpose of this lab is to simulate, using the correct physical principles and results from Lab 1, a model of charge tape using lines of charge as opposed to point charges. There are 4 relevant fundamental physical principles for this lab. The first is Newton's second law. This allows us in this lab to determine the net force on an object, which is important for the computation and also to obtain some of the results from Lab 1. Gravitational force near Earth's surface. The gravity constant is used in tandem with Newton's second law, and this helps to establish one of the forces acting on the charge tape. Knowing this force helps with computation and determining needed values. The next physical principle was Coulomb's law, also known as the electric force. This explains the force between 2 electric charges. The force depends on the size of the charges and the distance between them. The force increases if the charges are larger or closer together, and it decreases if the charges are smaller or further apart. Coulomb's constant is a useful value, and it allows us to determine, with Coulomb's law, excess and deficient electron charge later on in the experiment. The equations that correspond to Newton's second law, gravitational force, and Coulomb's law are shown on the left of the slide. The new fundamental physical principle for this lab is the electric field of a rod. Treating the U-tape as a rod with uniform charge allows us to create a computational model that more accurately determines the excess charge on the tape. In real life, tape is not a point charge, so being able to model the tape as lines of charge should prove a more accurate measurement. Preview of the results is shown on the left of the slide. From Lab 1, we saw that the charge tape has a net positive charge and had a tape charge and deficient electron charge as shown. Using the new lines of charge model, we can find the actual tape charge to be 19.06 times 10 to the negative 9 coulombs, and this means that the tape was deficient of 1.1925 times 10 to the negative 27 electrons. The images below show some of the details of the experiment from Lab 1. From Lab 1, we basically created 2 pieces of U-tape, and we tested the charge of one of the pieces of U-tape using my hand, the other U-tape, and a plastic pen. The data was recorded, and code was created, and the findings predicted and observed values were compared. For this lab, we used the results and observations from the previous lab in tandem with GlowScript and the equation for the electric field of a rod in order to computationally model 2 lines of charge. The results of this computational model were then taken and compared with the findings from Lab 1. The next step was to answer supplemental questions and make conclusions. Many of the important assumptions for this lab were also taken from Lab 1, but I will reiterate some of them as well as explain new ones. We had to assume the tape acts as a point charge for Lab 1. We had to assume both U-tapes are the exact same size. There was no air resistance. For Lab 2, we had to assume the tape takes the shape of a rod, and that the charge of the tape is evenly distributed along the length of this rod. A few relevant observations from Lab 1 that were used to help in this lab are described below. So we observed that the U-tapes repelled each other. The U-tape attracted my hand, U-tape attract the plastic pin, and the U-tapes on the tower repel each other as well. The first model below shows the point charge model, and the second actually shows the model for lines of charge. Some of the initial conditions and details for the lab are shown. The system is the charged U-tape. The surroundings is the second U-tape, Earth, and basically everything else. Some of the values derived from Lab 1 and from measurements from Lab 1 that were used in this lab are tape mass, tape length, tape width, tape surface area, tape separation distance, number of atoms on the tape, and the original charge and deficient electrons on the tape from Lab 1. The image below shows the calculations used to get those initial charges on the tape and deficient electrons. The first couple of lines of code were used to establish the constants that would be utilized throughout the rest of the computational model. And the next section of the code was used to create the electric field of a single point charge. Later sections of code will use this electric field n number of times in order to simulate a line charge. Lines 82 and 83 of the code were used to create electric field arrows. This is also where I established the value of the number of point charges to simulate. The code beginning at line 113 uses the force of the electric field equation. The code in this section simulates the process of iterating an integral n number of times in order to add up the total electric forces of both the top tape on the bottom tape and the bottom tape on the top tape. This final section of code simply creates the electric force and gravity arrows and outputs the results of the computational model as text. The results of the computational model can be shown here. The model outputs equal and opposite forces, which means that the system was in equilibrium. This suggests that the values for input charge, Q, and other necessary constants are accurate. It's important to reiterate that the system must be in equilibrium for the tape to float. Knowing this, we can set gravity equal to the equation for a uniformly charged rod and rearrange to solve for Q. This results that Q is 19.06 times 10 to the negative 9 coulomb. Further calculation using formulas from Lab 1 would give the U-tape a deficiency of 1.19 times 10 to the negative 27 electrons. These results differ pretty substantially from Lab 1, which can be expanded upon further in the conclusion. Despite the computational model depicting equal and opposite forces, there are possible sources of error that may call into question the exactness of this experiment. And these errors could include inaccurate measurements in tape size, width, and etc., and tape separation distance. There could have been rounding errors in calculations, incorrect calculations, incorrect utilization of physical principles, error in computational models, misinterpreted calculations and results, and mismanagement of charged tape. What if I had modeled each of my tapes as a single point charge like in the previous lab? In order to answer this question, I took my computational model from Lab 1, and instead of using an equation to calculate Q, I input the Q found in Lab 2. Images of the results are shown to the right, with the top image being the new point charge model. A comparison of all three values with their relevant charges of the tape and deficient electrons can be shown. Three computational models' results differ due to the fact that each model is effectively using different calculations. Lab 1's point charge model only considers the charge of the U-tape at a single point. Lab 2's line model takes into account many uniform charges spread across the length of the tape, which would provide a more accurate result. Lab 2's point charge model goes back to using the more broad formula present in Lab 1, meaning that even with the same charge as calculated in Lab 2, the results were bound to differ. Simply put, the line charge model is the most accurate due to the tape being shaped closer to a rod in real life than a point charge.